In this lecture, we're going to start with a discussion of a stable star solution, a solution of Einstein equation which describes a spherically symmetric, stable star. In literature, this solution is referred as interior solution. We assume that the star is a ball of matter, and inside this ball, we have non-zero energy momentum tensor. T mu is not zero. Outside it, T mu is zero. And everywhere we assume that lambda, cosmological constant, is zero, everywhere. So, to have a stable star, so far we have encountered several different choices for the energy momentum tensor, and one of the peculiar energy momentum tensors was the energy momentum tensor of a dust. But that one is just a collection of particles which do not interact with each other and do not create any pressure. So that one is not suitable for the problem that we are considering, because we need to have such a matter which creates some pressure on general physical grounds. We need to have something which creates a pressure such that it doesn't allow this body to collapse, because gravity is attractive force, so everything is tending to shrink, while pressure pushes it away to make it stable. So we start with the definition of the energy momentum tensor for the perfect fluid, the one which describes a matter with a pressure. So for that fluid, for the perfect fluid, energy momentum tensor is as follows, where x bar is 4 vector, which is t and x. So, and so it is equal to rho, which is a function of x, in general, u mu, which is a velocity, 4-velocity field of the fluid. U mu and u nu is a 4-velocity field, plus pressure times u mu of x, u nu of x, minus g mu nu, which is a metric tensor of x. So why this is pressure and why this is energy density is going to be obvious soon. Now we start to explain why this is energy momentum tensor for the perfect fluid. But recall that we have already encountered when p is equal to 0, this is the energy momentum tensor of a dust that we have encountered already. But now let us consider this energy momentum tensor in the reference frame where the species, where the fluid is static. In such a reference frame, u mu of x is nothing but g 0, 0 minus half 0, 0, 0. The reason for having this is because we have to have u mu is equal to 1, which follows from the definition of the 4-velocity. So this is a form of the vector for velocity in the reference frame where the fluid is static. And in such a reference frame, the T mu nu, the matrix of the tensor, let me write this as G nu alpha, T mu alpha. So we want to consider the matrix of this tensor. It's not hard to see that the matrix of this tensor has the following form. It's diagonal, as it follows from here. It's diagonal with content like this, minus rho minus p minus p minus p. Already from this form of the tensor, of the energy momentum tensor, it should be apparent for those who have been studying, who have studied classical electrodynamics and special theory of relativity. Already this form tells us that this is energy density and this is pressure. But let us do a bit more. I mean, we're going to give more explanations why this is an energy momentum tensor for a fluid, for relativistic fluid. So let us consider the conservation of this energy momentum tensor. The conservation law for this energy momentum tensor is as follows. And for this particular form, if we substitute it there, it acquires the following form, this conservation condition. It's u mu d mu u nu plus d mu rho plus p u mu u nu minus d nu p. So this is a conservation condition. And now if we multiply both sides of this equation on u nu and use the fact that u nu times u nu is 1, and as follows from this, we have that u nu d mu u nu is 0. So using this and this, after multiplication of this equality on u nu, we obtain the following equation, that d mu acting on rho plus p u mu minus u mu d mu p, and opening this up, we obtain that this is d mu of rho u mu plus p d mu u mu. So we obtain this equation. This is a relativistic, covariant extension of the standard matter conservation law, which has the following form: rho u mu is equal to 0. So this is just a continuity equation. This is a continuity equation in flat space, and this is a relativistic covariant extension of this equation. Indeed, first of all, if we go to covariantization, this derivative becomes covariant, so we obtain this part. And also, in addition, we have to have this part in the presence of pressure in relativistic limit for the following reason. In non-relativistic limit, pressure is always much less than the energy density, for the same reason why non-relativistic kinetic energy is much less than mc squared. So from the relativistic energy due to mass. So this is for the same reason is smaller than rho. So in non-relativistic limit we would neglect this, and we will obtain this equation, which in three-dimensional notations is nothing but dt rho plus divergence of rho v equals to 0. So the obtained equation has obvious interpretation of the relativistic covariant extension of the continuity equation. So from the condition of the conservation of this energy momentum tensor, plus p u mu u nu minus g mu nu, from the condition of the conservation of this energy momentum tensor, we have obtained these two equations, well, which are one follows from the other. This equation, u mu d mu u nu plus d mu rho plus p u mu u nu minus d nu p. So this is equal to 0, and the equation that d mu rho u mu plus p d mu u mu is equal to 0. So this is the last equation is covariant relativistic extension of the continuity equation. So if we use this equation here, we obtain the following relation, that rho plus P times U mu d mu U nu is equal to delta nu alpha minus U alpha U nu acting on d alpha P. So, and this, if one looks to the matrix of this tensor, it is diagonal 0, 1, 1, 1. Hence, this is a projector on the spatial part of the space-time. And we declare that this is a relativistic covariant extension of the Euler equation. Euler equation has the following form. Euler equation is nothing but rho dt v plus v times differential of v equal to minus p. So this is just a relativistic extension of this equation. This is nothing but, the Euler equation is nothing that Newton's second law, ma equals to f, attributed to the unit volume. Indeed, if we divide by volume both sides of this equation, and recall that pressure is nothing but the force attributed per unit area, and this is mass attributed per unit volume, and this is nothing but acceleration, which is dv over dt, but v is a velocity field, so it depends on t, x of t. So if we apply this, we obtain that this is dt v plus di v times dt xi. Well, this is nothing but dt v plus v times the gradient of v. So this equation is Euler equation, which has obvious meaning. This equation is its relativistic extension. And finally, the Euler equation, this equation can be written in this form. It is dt rho vi plus dj t I j equals to 0 for t I j equal to rho vi vj plus p delta I j. So this equation is equivalent to this one. And perhaps I have to stress, just finally, that this is equivalent to this. I mean, this is just tensor notation for the gradient vector. Anyway, so all in all, what I have said should convince one that this tensor is a tensor describing perfect fluid. And what remains to be done to specify the fluid is to give one the equation of state. Equation of state is the equation relating rho and p. So equation relating the pressure and density. If we specify this, we specify the fluid completely with this tensor.